Hello, good morning, and welcome to a new food4Rhino webinar. Today in a different time than normally we do this in the evenings, but we hope it's also a good time. And as always, the webinar is being recorded. We will upload it later to our food4Rhino webinars YouTube channel. In case you miss a part of it, you can always access that channel and watch all of our webinars. Welcome to Christian Waldvogel, CEO of Spherene and co-founder, and to Daniel Bachmann, Chief Innovation Officer. Christian and Daniel will explain to us what is Spherene, what is Spherene Metamaterial, and what it adds to the world of the additive manufacturing. And of course, how it integrates with Rhino, what are the possibilities, when there will be a release candidate, what are the next events, some case studies, and of course, a live demo. Please feel free to use the chat. I will collect the questions, and then during the last 10-15 minutes of this webinar, I can pass the questions to Christian and Daniel. And yeah, thanks again for being one of the viewers of this webinar series. Thanks, Christian and Daniel. We are eager to see what Spherene brings to the Rhino world and to the additive manufacturing industry. So feel free to start with your presentation. Thank you.
Hello, everyone. Thank you, Carlos, for having us. It's great to see so many of you here. Familiar faces as well, and we are very happy to be able to present now the almost finished software, which is going to be released as a released candidate very soon. All of this after 1 year of being in alpha and beta versions, with some 400 users having tested it, doing all together about 10,000 computations. So we are very happy to have a stable version of our software. Now, Spherene was founded in 2018. We have currently 4 employees. All of them are in this call. You have heard of Daniel Bachmann already, Ralf Berci, who is engineering the software, and Alex Kühne, who is doing business development and strategy, and is a co-leader, are also here and are happy to take your questions as well if they go in that direction. But before we go more into, let's say, introductory stuff, let me tell you about Spherene, what it is. So we found this new type of minimal surface, which shares with the ones you know, like gyroid, that it's a minimal surface, meaning it has zero mean curvature at all places. It has 2 labyrinths, and that's it. From there, our thing, which we call ADMS, adaptive density minimal surface, is completely different. It adapts to the shape. So it is being computed outside in, meaning that whatever shape you use that you will fill with this structure, it will end in a way correctly on the outside. You could call this surface conformal. And so we are producing the only surface conformal minimal surface around. We can change the density and other parameters at every spot very easily without losing the fact that it is a minimal surface. It's random from up close, reproducible though, but it is regular as a whole. And this means that it is a metamaterial. It behaves like bulk material. It retains all the characteristics of a bulk material, but with our ability to change it so that it adapts to whatever needs one might have. This leads to the possibilities of, let's say, building a part out of steel, but with the characteristics of aluminum, with the weight and also the stiffness of aluminum. So to make this a little bit less abstract, I would like to hand over to Daniel, who will show you a few things directly with images and then in Rhino.
Thank you, Christian, and thank you, Carlos and McNeil, for having us, and thank you guys for joining us. So I share my screen now, and let's see how it goes. So this is what Christian told you before, that we have this difference between a gyroid and our Spherene metamaterial, where the gyroid, for example, if you have it cut out with the surface, introduces the forces that you apply into different directions, because the gyroid always has a specific end where you cut it, where it is joined with the surface. Also, the distance where you have these joints with the surface varies a lot. On the other hand, with Spherene, we have a mostly regular distance where we join to a surface, to an outside surface. And this also leads through the perpendicularity, how we close up to that surface. So we follow it exactly and try always to be perpendicular. We introduce any force from any direction, from any complicated object directly into the structure, where it will be evenly distributed. So it behaves really like a bulk material. So what Christian described before, I have some images here. So we have this isotropy, meaning from all directions, it behaves like force introducing, or it simplifies the introducing of force. We have this surface conformity. You see all these volcanoes following the surface. And if you would put this into a car bumper, for example, and you crush it into a wall, all these little structures will still hold up most of the force that has been lost from the crushing of a little part of it. Then we have fields where we can control density and thickness. And as you see here, we do that in a very organic way. We do not distort any unit cells with a gyroid or TPMS structure in it. This always tries to be the inside or the outside of a sphere, and therefore we grow into your shape. So you do not, as in other software or applications, where you first make a TPMS or a gyroid and then you cut away your shape. Here you design your shape and your design intent, and our structure grows inside. We can combine any of our fields with any of our mesh modifiers. So here you see a cavity feature that is repulsing the minimal surface. Imagine you make a huge object for a movie prop where you want to have actors standing up on it. You can make it hollow, so you do not print the inside, but on the outside we have a super strong thin shell with our Spherene structure that is distributing the force all over. So it prints fast and it is very strong and lightweight. Then on the left side here, you see two features for modifiers. You can introduce a mesh and tell this mesh to make a skin or a hull, close up specific areas of your design. I will demo that later. So here some examples. Our method works in any printing method in any material. We test so FDM, SLS, SLM. This is a aluminum part. Then we have a plastic part that was made in SLS. Beautifully described here the surface conformity, how it closes up to the surface. And also here, how fast we can make these transitions. They look really organic, like a coral or a real bone structure. Then René Medel from Framas made this prototype for a shoe. It can be printed in SLS, it can be printed in FDM. You can depowder everything because we have these two chambers that do not enclose any powder or resin. So you can just shake it out or use compressed air or chemical agents to clean the inside. We can go really small and high performance materials. So this is a titanium material, different kind of resins. Now, how does this look in Rhino? So we worked really hard to make the best in class design tool. We provide you with an integration of Spherene, where in Rhino you work either with these points that you see here. These points represent our fields, like density field, thickness field, cavity field, and so on. Then on the other hand, we work with mesh modifiers. So this sphere represents a so-called envelope, we named that. And inside of this volume, this Spherene structure happens. So on the left side, you see these black points with some values. These are radius values. So imagine little spheres around each of these points. Then on the bottom here, we have this blue dot. This represents a density point. So we need only one point and these few points here and this mesh to, by one button click, make this. So you see this is a hollow sphere and it has kind of windows all around. And this is a matter of 2 minutes of design work that I have to do. You can import from any CAD software, just export your CAD part as a mesh, import it in Rhino, and just work on your design. You will see how crazy fast and easy that is. So it's a huge time saver. So here you see the so-called envelope and a Spherene structure inside. Then on the next one, we have a mesh modifier called DFN, defeatured envelope. This changes the outcome on the outside. So you see here, we don't have these volcanoes that we have seen before. We can change this DFN to mix kind of the outside look together with a simple mesh. Then you see a gradient of density. On the left side, we have these few numbers on points in position in space. On the right side also, and in between, we change from this 5.6 volume fraction to a 22% volume fraction in an organic way. The same is possible with the wall thickness. So these magenta dots represent wall thickness. We go from 0.4 millimeters to 3 millimeters here. Then we have a surface bias. So we can also take the minimal surface that is really strong in its ideal position, and we can move it outside to the left or right and weaken it up. The effect that you see is small holes with long necks or big holes with short necks. And everything again in an organic fashion. Here you see some use of these cavity points. You can imagine an array on a line, on a curve, to make a cable channel so that the cable through this smooth surface will not be damaged without modeling that in CAD. So you could do that, but this is another way how to creatively use our tools. Then we have boundary meshes. So that are simple meshes that can be volumes or just sheets, little dimensionless, or sheets without thickness. And we can tell them to thicken up or separate our volumes. So I will now show you how our release candidate 1 looks like. So that is, we had alpha and beta version since like over a year now. And very, very soon, as Christian will tell you later, we will release this version. So what is new? We have a toolbar with some really nice icons. So if you do not speak English, you can access these icons by image. So that's the main place where our Spherene stuff happens. The other space is in the layer system, and the next space you will see in the demo. So I told you we need a mesh. I create a sphere, a mesh sphere with a diameter of 60 millimeters. Now I create a new project. I click this button here, call it sphere. Now watch this space here of the layer structure. I will be asked to select an envelope mesh, so I select this one. What happened is Spherene already populated our project name containing a meshes layer and a fields layer. In the mesh layer, we have an envelope, that is this mesh here, and the field layer is populated with the density fields with this point here. There is a number inside, 5.6. What does this mean? Together with the wall thickness that we target, this volume will be a Spherene later that is 95% lighter than this volume that we see here. So you can think about this. Christian will go into details later for that. So just bear with me. Now I click this button here, Spherene Compute. So I created the mesh, I created the project, and now I'm already making a Spherene. So here I can enter a default wall thickness. I can have a single surface that is a surface without wall thickness. This computes faster, so I can iterate on my densities, and when I'm happy with that, I can start thickening up. I do now simultaneously both the single surface and the solid surface. We have some color schemes, so I activate that for each. In the single surface, we show the mean curvature. I can give it a name if I want. And now this version I show you now works a little bit faster than the release version. For demonstration's sake, this is our development server. The results that you can expect back from this example will calculate about 30 seconds in the official release version. So this goes maybe 17 seconds or so. So we already have a result back. It made a new layer here called Spherenes. So all your Spherenes that you generate will land in this layer structure. You see here we have a single surface and a solid surface. Let's hide the original envelope and inspect what we have. The single surface looks like this. It has no wall thickness. It has some coloring here, and this coloring represents the quality of the surface. Now imagine I told you before that we have the insides and outsides of spheres that we interconnect. At each of these interconnection, we have to grow the connection, so it will be always the best possible that is algorithmically feasible to do so. So it's almost perfect, and this is what these colors represent here. So you can check the quality of your surface. Then on the other hand, we have the solid surface that has thickened up to 0.4 millimeters. The interesting thing with this color scheme is you see the two volumes. Imagine this now to be an engineering part, a heat exchanger. In the orange part, you can have water flowing. In the gray part, you can have air flowing. And all in all, it is a structural part that is very rigid. So you can imagine your heat exchanger not being only a cylinder, it can also be like in a frame of an airplane, for example, and has real functionality inside. The computation button, if every time I click it, it will generate an output here. So I can work on doing my design while it is calculating. So what I do now, I make a gradient. I just copy this point here and make a gradient from 5 to 16 volume percentage. I place this in the middle. The more points you use here, the denser your so-called force field will be. Let's shade this so that you see better what I do. Now I introduced the density gradient, and on the other axis, I want to introduce a thickness gradient. So here I can add field points. I have a selection of different field points. I select thickness, place 1 point here, 1 point here, double click the right one. And what this means, please do a 0.4 millimeter to 2 millimeter wall thickness change in this axis, do a density change in the other axis. Now let's calculate that and name this gradient, compute only the solid surface. So now this is all cool. We have this open structure. Let's hide these fields. So we have the density and thickness field, and I will show you now what happens with the mesh modifiers that we have. So this is our envelope. I will use the same envelope and add a boundary now. Click the boundary button, click this object here. What this did, it made a copy of my envelope and changed the color and made this layer here. If I would give this object here now a wall thickness, it will be an infill. But this is boring. We do something more complicated. So let's use some Rhino tools and cut this apart. So in CAD, you can prepare all these design intentions that you have. And as you see, I do not even think about the structure itself that it's generating. I always think about the my design intent. I used mesh split now and split this mesh with these curves. So let's delete these guys and let's see. So we have now separated objects, all right? Now I told you we have the toolbar as Spherene tool, we have the layer, and now I introduce this attribute user text because here we have some functionality where we can tell an object to have a hull thickness, for example, of 1 millimeters. We can tell this one also to have a hull of 1 millimeters, but I change a flag here to false. And I will not explain it now because you will see what it does in the result. So I have the back face and front face changed for these two objects. So one is false true and one is true false. And on this one, I leave the hull thickness to 0 and tell the structure to thicken up to that surface with a specific thickness. Let's calculate that. Let's call this boundary. And let's examine our previous results. So this was the first one that we created. And now let's check out the one with the gradient. We have a density gradient that has lower density on the bottom and higher on the top. On the left side, you see a wall thickness of 0.4. On the right side, a wall thickness of 2 millimeters. And if I shade this, you can see how this looks. And while it is computing the result, I introduce a cavity field on the bottom here. I have to activate this one to see. And this is like behaving like a sphere. So I tell this to have 60 millimeters diameter and I compute that. So let's examine the output of the boundaries. So it didn't do what I do. This morning we encountered a bug. I hoped it worked. So the true false flags ignored what I said. This will be fixed on Monday. But see that we have closed the wall with 1 millimeter wall thickness using a simple mesh. So I made now something really complicated in about 10 minutes or so, without even having to deal with any formulas or anything. Let's see this one with the cavity. Cool thing now is this is a one object that is ready to print. You do not have to Boolean anything. It comes out nicely right out of the box. And now I want to give it over to Christian. And he shows you now what this means. I showed you now a little sphere, but what amazing things can you do with it? Christian explains that.
Thank you, Daniel. Let me just switch over. Can you see this? Okay, so just to quickly circle back, what you see here are the three main configuration parameters that we use. So density, increasing density, then going to the left or the right with the surface bias, and the thickness up and down. And so the colors that you see on these samples here, they are also the colors that you'll see on your meshes if you choose to display, let's say, surface bias on your single surface. Now, we tested these. Oops. Now, here we go. We tested these samples, and we see here that this all behaves extremely regularly and following always the same pattern, which I hope in quite not too much time we'll be able to provide a formula that predicts the stress and strain behavior of a surface. One thing that's interesting to note is that the whole thing, because it is so regular, behaves with a density series that is the same as the numbers you might know from the old days when the aperture on a photo camera was still adjusted manually, right? So to make a meaningful gradient in density, you can use those numbers. So to go from 2 to 2.8 to 4 to 5.6, etc., will give meaningful differences. Obviously, you can choose densities at any value. You can do 8 and 7.9, but you won't see that much of a difference. So this square root of 2 series kind of helps you when you want to go a bit thicker or a bit less thick. Now, I want to show you a little project that one could do. We're going to do a small fixture. So we have a design space here, some forces that are needed to be countered by the part, and some interfaces where screws are going to be entered. We designed an envelope using, you could say, a combination of design, optical design, design intent, some engineering knowledge, I forget the word. But you could also use a simplified version of topology optimization, obviously, right? So we came up with this shape, and we designed some interfaces as solid bodies. I did all that CAD work beforehand, so we don't have to deal with that during the presentation. Now, we simulated the loads that we're going to get on this envelope, as if the envelope was a piece of solid material. And because it's so thin, and because it's a demo, we just use a single simulation, so front and back are the same. That wouldn't be the case, obviously. We do have some material that is given, aluminum in this case, which has a yield strength of 255 And when we take into account the safety factor of 1.4, square root of 2, obviously, we see that we have a maximum stress that we can allow of 180 MPa. And we need to print at 0.6 millimeter thickness. So if we look at the actual stresses that we see, this is obviously all ballpark. We're doing this like off the cuff, right? So we see we have around 30 MPa in the light green areas, going down to 6 MPa in the dark blue. I just see that the image shifted here. I'm so sorry. This is I should move this over a little bit. Okay, now it's correct again. Now we know we have 30 MPa. We cannot go above 180, right? So we do a simple computation. We calculate 180 divided by 30, gives us 6. That means that 100% density, full material bulk, divided by 6 is 16%. That leads us to the knowledge, okay, we can go for a density of 16 at the most intense places. Now, from this, we are ready to go to do a project to generate a spherene. So we'll click on the new project button here. We call this bracket. And we select our envelope. Now, as we saw before, we have received a new layer here called bracket with an envelope mesh, right? Now we have to go and do the densities. So we know that the green here needs to be 16. So I'll press on this button here, say I want to do a new density point, I enter 16 and populate this here with a few such points. Doesn't need to be too many. And for the sake of simplicity, I'm going to group them real quick. Then we know that from the cheat sheet we saw before, where I showed the densities, we know what the feature size is going to be. And we know that at 3.3, there's almost no material going to be left. So we know that 11 is kind of good in the actual size of this bracket. So we're going to do the rest at density 11. So that means from here on, we're going to have 11, right? And out here as well. And I was a bit oblivious to that we need 16 here as well. So that's our density field. Let's just, we see that we have a new layer here, density, right? So I'm just going to quickly select all those. Group them together. We don't need that. Sorry, wrong. Don't need that one here. So if we look at it from the top, we see that these densities are obviously now on the surface and just on one side. And because we're doing it the simple way now, we're just going to repeat them across the whole depth of of the part so that we get an even density distribution again. As we heard before, we are ready to go. So we're computing. Now, take note here in the density reference thickness, I entered 0.6 because that's what we have to think of the densities being calculated for a thickness of 0.6. That's why I put it up here. We're going to show the mean curvature here in the single surface and call this run 1, for example, and go. So this is running now. While it is computing, we can continue our work with the stuff that is going to be relevant in the 2D, the thickened version, the 3D version, sorry. So as you can see, we have these boundaries here that are prepared. So we're going to select them, go to this button here, say add boundary, and we did. So let's remove them from here and show them in the bracket again. Oh, we have the result already. We're going to talk about that later. So these are our boundaries. I'm going to specify them in the user text up here. We leave everything at default for now. Maybe we can do the target thickness a little bit thinner. Because they're all 3D objects, solid ones, I let the hull thickness at 0, which means they're just going to be solid with no additional thickening. Now, if we go back to the result that we have here, we see that that we have received this result, which has the densities that are needed to counter the stresses that we will expect. And we see one bad thing, and that's these outer regions here. They produce problems in printability. So to counter this, I have prepared, a little piece here. I just cut a section through the envelope and created these two small two-dimensional lines that I'm going to add as boundaries as well. So I just did that. I remove it from the printability layer, and we see we have those boundaries. And now they are going to receive a hull thickness, because otherwise they would just kind of create or cause the ADMS structure to thicken. We want them to really show, so we give it a thickness of 0.9, and that's it. Now we are computing again. We want the single surface with the density shown, and we want the solid surface, and we call this run 2. And we'll go. Now, in the meantime, let's look at the 2D surface. We see here these colors. As Daniel mentioned, they implicate the degree of mean curvature 0, and we see that in some points it's not ideal. However, this is a for us, we just balanced the time it takes to compute something and the surface quality or the minimal the mean curvature quality you get. So in later versions, there will be possibilities to adjust this to take accept longer computation times but get better curvature. Now we see we're at 3 of 6 steps in the solid computation. 5 of 6, so we're almost there. And now we're just waiting for the result to be delivered. Here it is. So this is now our fixture. It has this boundary at the side, which makes sure that it's printable everywhere. It has the density that we needed. The stiffness in this direction is actually covered by a mixture of the design of the envelope and what we told it to do. And we have all the interfaces with nice connections to it. And it's printable like that. And to take things one step further, this is actually a bracket that we did for the European Space Agency. And it did survive all the shaking up to 1000 Gs. So naturally, what we see here is a first ballpark iteration. It's like a dimensioning that kind of gives you the first point to start. And from this to printing it and putting it on the shaker, there were a few iterations that involved validation on simulation. And so this will still be necessary, but you are very quickly very near to a potentially functioning result. And speaking of simulation, if there's anyone on the call that works for a company that is willing to accept the challenge to work with us to integrate some sort of sheet and solid simulation on that, please come talk to us. And with that, I would like to conclude my part. And I think we're going to be handing over to you guys for questions.
Many thanks, Christian and Daniel. Amazing. I wish you a lot of luck with the race candidate. I think it's an amazing product for Rhino. And also we will see more at the upcoming CD FAM conference in Berlin, beginning of May. And yeah, now it's turn for questions. There were already a few on the chat that Daniel and Ralph Bershi answer, but so that the people can hear these questions again. Yeah, for example, Moritz Bauer asked if the boundary can only be generated on one side of the labyrinth, or if you can also close one side, for example, for a heat exchanger.
Yes, you can. So there were these parameters, front and back, that were both set to true. You can set them to false, and then only one of the labyrinths is applied, so to say.
Okay, nice. This is what Daniel answered already, but again, so if people are not reading the chat, it's always nice to explain this with words. Also, yeah, Daniel remarked that you can achieve also this all of this with scripting in Grasshopper. So you open it. I mean, you can not only use the Rhino interface, you can also use Grasshopper for Spherene. That's great. And yeah, Nada Ashi, a good friend Nada, asked how you should decide the thickness of your object based on the object size or on the requirements, I guess, on the printing requirements.
Well, first of all, on the printing requirements, what is the minimal thickness that your printer can deliver safely? And then second is obviously the stiffness. So to make something stiffer, you can either increase the thickness or increase the density. Now, because forces generally flow on the surface of things and not in the interior, it's actually more efficient to increase the density than to increase the thickness. But as I said, this needs to be kind of like verified on a case-per-case basis. So in the case of the ESA bracket, what we actually did is once we had settled on a single surface design, we simulated that and then slightly adjusted the thickness in different places. So when we saw that there was a region where it was critical, we just added like a 1/10 of a millimeter of thickness locally.
Thanks. Then another question by Nada. She was asking Daniel how you can hollow an object to achieve a lighter result.
So we used this cavity feature, so that's that one. Okay, it's all like in the other direction. But place a cavity point, make it one or multiple points, make it big enough, and this will hollow it out. Makes it still printable on the inside, and that's how I would do it. Or you can also model a hollow object directly in your design.
Nice.
Yeah.
Cool. Thanks.
Or you just kind of go down with the density.
That's another option. Okay. Then another question by Nayara Rodriguez. Thank you very much. Is there a way of obtaining the negative volume without applying any Boolean operations?
Yes.
I'm thinking about evaluating the fluid flow behavior, for example.
Yes. So at the moment, we have two result types, single surface and solid surface. There's a third result type, which will be released very soon, which is the labyrinth, which is exactly what you're asking for. So the empty spaces as solids. That's very near. It's just we had to limit ourselves to release what's really been tested. So, but we don't have to. It's developed. It just needs to.
Okay.
Please get in touch with us if you do fluid simulation. We are interested what you do with it, and we will help. We will assist you in your journey and learn from each other.
Thank you. Okay, that's a tricky question from also our good friend Peter Donders. Hello from Belgium. Is there a pricing set yet?
Yes, there is. Let's get Alex to talk.
Okay, I guess first.
Sorry?
Sorry, yes.
Hi, everyone. I'm Alex. I'm here at Spherene since about 1 year. I do business development and go-to-market strategy. We have a price indeed. We have 3 different tiers. We have an educational license, which is non-commercial. That starts at 350 per year per user. Then we have a studio license, which is 1,250 a year. That's up to 20 employees on the company size. And then we have 20 employees and above is 4,750 a year. This includes obviously all the computing as well, the server costs that we have on our side. And in the first year, we will give a 30% discount.
Thank you. I guess you will put these prices soon on your website as well, right? So that it will be easier for people to check. Cool. And this is a bit related because you mentioned the cost of the server. Afonso Gonçalves, thanks you for the presentation and congratulates you on creating this such an intuitive and user-friendly tool. And he asks if in the future, if there will be a way to increase computation limits, if it will be server-side or client-based.
So it's always going to be server-side. The computation limits, I mean, obviously we want to do it as quickly as possible. At the moment, if we kind of really use up all the computation limits that are available, we're receiving models that cannot be handled in an efficient way by today's computers. So obviously, if there is like an application where a company or well, I say a company wants to do extremely complex, extremely large things, then we can obviously talk about installing a dedicated server on site or in our cloud that has even more power.
Okay, thank you. So that means you need to be always online, right?
No, you need to be online to send.
To send, yeah.
Once it's sent, you can go offline and then get your results when you go online again.
Okay, understood. Thank you. Then a very wide question by Arash Yagubi. What's your roadmap for where you want to be in terms of capabilities in 1 to 3 years?
So we have lots of features in the back of our heads that we plan on implementing, which I can't share at the moment. It wouldn't be fun otherwise. One of the things that we're working on is to further understand how the metamaterial actually behaves. What are the connections between different behavior in different materials, also behavior that's beyond the breaking point. And so the biggest change that I expect within the next year is a more detailed engineering tools, where you can directly relate simulation results and requirements to densities and thicknesses, such that the mechanical behavior is within your tolerances. Other than that, we are also looking for other partners beyond Rhino with a tear in our eyes, because we think that Rhino is actually the best tool, but we feel the pull that some engineers want to work from within other softwares. So that is one point where we're also going to expand our operations into.
They could also buy Rhino.
saying that, like the user interface, as you have seen, what the experience is, how easy it is, it's very hard to replicate that in other software. So this, what we have in Rhino, is our reference design. So if we can have this workflow in any other like envelope software, we'd be happy to do that. Or if somebody wants to do that, we're also happy to talk about helping that out. So we have this cloud algorithm, we have an API that we can talk through. This is what we do with Rhino. So all these little modules are building up together. So standalone applications could be something in future, but at the moment, let's release, and maybe Christian can tell you later what that could mean. And we concentrate of you having a good transition into it, making it really smooth and giving our support, and then we ramp up.
By the way, related to your answer, David Weiser asks, how long will be the free release candidate be available?
So we are planning to release the version 1 early in May, and we'll be offering a 21-day free trial for everyone who kind of like from that moment on. Also everybody that has been testing now for the last year, they will also have these 21 days. Right.
So reason about that is also we are ramping up the resellers. So we are not directly selling if possible. So if you're in a country that has no reseller, we are trying to make the sale direct. But our plan is now in the background, what is happening, having all resellers on board, make the discussions, agreements, have everything ready in their web shops. And this takes time, and this will also decide how long it goes for the release. And for that, we thought, okay, let's show you the application that you can buy in a release candidate 1, fix some bugs during that. But we have this new toolbar We have a new documentation going. We have shaped the algorithm that it is faster and more precise. So all this you can experience now, even as alpha and beta tester. And then there will be a switch.
Okay, thanks. And a few more questions. This one by Marcel Gord. Is it possible to control the mesh skeleton to prevent dead volumes, for example, in a heat or gas exchanger along the boundaries?
Yes, we don't have basically dead volumes, but since you change the wall thickness around complicated boundaries, they might happen, but in that case, it will be like small entrapped resin or powder. That is very small compared to other solutions. Maybe Christian, you have some more insight.
I mean, one of the, as I said, a spherene is basically random. And that's why it's isotropic. That's why it's so good. Now, there's a random seed which lets you recreate the same geometry twice. But as you saw, when we first computed the single surface in my example, we then worked on the 3D part. And in this step, the single surface didn't change anymore. That means that you can use the single surface and its interface to the envelope to identify such closed shapes and then correct them using operations that won't change the single surface. And these are the boundaries and details that are going to come up later on, and the thickness field. So if you keep the surface bias field and the density field and the cavity field constant, then the geometry is going to be the same. And so in that space, you can find problems and act accordingly. Does that help?
If it doesn't, because there are a few more questions, please contact the Spherene team through their tech support channels on their website, through food4Rhino, etc. But maybe Daniel wants to say someone else.
This is very important. Our support, you see these 4 guys from Spherene here. So we cannot manage 100 of emails. But what we have is we have a Discord channel for support and community building. Share your work there and talk directly to us there, or have other customers help each other. So this is why we choose the way to put it on Discord. I want to mention that because it's an important factor. How do you get in touch with us and who is responding?
Cool. And yeah, one more question. This one by Scott van der Ven. Why was the density 3.3 not needed to be specified in your example?
So if I would have gone to density 3.3, then there would not be very much geometry left, right? So it becomes unstable. So obviously, with more time, one could go down, right? Kind of do a few computation iterations and see how low we can go. If I would have gone to say, let's to 3.3 there, we would have received an object which is kind of like has the bottom interface hardly being touched. So that's why I didn't do that. But since these iterations are so quick, this is obviously not a problem to play around with.
Okay, and now we'll go very fast through the last questions because we reached 1 hour time. Is this CPU or GPU based? It's GPU, right? Or
it's a little bit of both.
Both.
Yes. Some routines are on the GPU, some are CPU based.
Okay.
But remember, the client, in this case, the Rhino plugin, just creates control commands, and everything else is happening on the cloud.
On the cloud. And there is a related question. If there is a standalone Rhino plugin without online servers, in case you had a lot of computing capabilities in
Well,
your company or at home.
This would go under the company special tier, where we would install a dedicated server on site. I mean, this can be done, but it's kind of a special case.
Okay. So many people are thanking you for your impressive presentation and product. And I was also posting here the link to the CDFAM conference in Berlin, where both McNeil and Spherene will be present. I think it will be a very nice conference on May 7th, 8th. And then, yeah, the very last question. The envelope to Spherene bond line looks more perpendicular and does not have curvature to tangency to support the surface, just such as creating a flange.
Yes, that can be done. Those are the two parameters that I didn't touch because of the demonstration time. Target thickness and blending distance and blending exponent. With those parameters, you can create a rounding off. It can be rather sharp, or it can be wide, or it can be straight, almost like a chamfer. You can do that. Also, one thing, you maybe saw that in the computation, we always did the solid surface in the draft mode, because again, it's about time. So if you go for the final mode, the mesh resolution will be larger. So especially these details will come out much better and clearer.
Perfect. And you already answered that Spherene is available for both Rhino 7 and 8, Windows and Mac. Also that there is a 21 days free trial. Some people are asking for a free version for hobbyists or students. You said there will be one, or I'm confused?
We have an education version.
Education, okay.
And let's see how it goes and what the community says, and then we can adjust. And also very, very, very important, this Monday at noon, we are switching to RC1, so release candidate 1. Existing users, please go then to our new help site, or you have already received an email from us to get the new toolbar, then update the plugin in the package manager, and you're ready to go. If something fails, contact us on Discord.
Perfect. So many thanks. I will upload this webinar, the recorded session, on YouTube, on our YouTube channel very soon, between today and Monday. Maybe I will do it on Monday, then I can send people a link to your website with the release candidate and with the recorded session. And again, many thanks for your time, for the very nice presentation, for the very nice product. See you in Berlin, and many thanks to all the viewers of this webinar that are clapping their hands and congratulating you. Thank you. Have a nice Friday afternoon, evening, and a very nice weekend. See you soon.
Thank you very much.
Well, thank you so much for showing up. And thanks to all our alpha and beta tester for kind of bearing with us all this time. It was very helpful.
And thanks Ralph for making this code.
Yes.
So he's the hero behind the algorithm.
Thank you. Bye.
Bye bye.
Thank you guys. Bye bye. Bye.